This video is about the gradient. Now, I went on to Google and typed in gradient images, and the images that came up were sort of interesting, just a bunch of colored panels, much like this one. So apparently the word gradient is widely used to describe gradients in color, as shown here. My use, sort of everyday use of gradient has been with regard to science. Here's a or a contour map of the Big Island showing the elevation going up Mauna Loa and Mauna Kea. My personal experience has been with regard to topographic gradients um, uh, involved with skiing or hiking or biking, and this shows some skiers contemplating going off a very steep gradient in a snowy slope. So, whatever your experience of the word gradient is, today we're going to formalize it with the mathematical definition of gradient. After viewing this video, you'll be able to identify the direction and magnitude of a gradient from a contour plot, for example, like this one. You'll also be able to compute the gradient of a 2D and 3D scalar field. So this is from Greenberg, section 6.16.4 on the gradient. And so if we have a scalar field, that is a scalar quantity that varies in 3D space, we would write the gradient of that scalar field as grad u, or using our del operator right next to u. So these are two ways of writing the gradient of u. Now the del operator is a very convenient way of understanding gradient. Remember that del in Cartesian coordinates is equal to, it's a vector operator. Let's see. Yeah, it's a vector operator. It's an operator with vector properties. So the derivative with respect to x is associated with the direction in the I hat direction. The derivative with respect to y is directed in the j hat direction, and then the derivative with respect to z is directed in the k hat direction for this del operator. So when we write del u, we're applying that operator to the scalar field. So we take the partial derivative of u with respect to x, and that gives the component of the gradient in the I hat direction. Likewise, the partial with respect to y gives the component of the gradient vector in the j hat direction, and the partial with respect to z gives the component in the k hat direction. So this gradient is a vector quantity. It converts a scalar quantity into a vector quantity. So let's talk about, what does this mean? What is meant by grad u, by this vector quantity that I'm describing here? So let's sketch some contours of u. Let's see. So we have an x-axis and a y-axis, and let's see. What am I gonna? I guess my contours of u will be in red here. And these are lines of constant u values, for example. Okay, so along this first line, u might be 1 The second line, u might be 2, and so forth. So these are contours of u, or curves of constant u. So everywhere along those curves, u, this scalar quantity, has a constant value. And so u could be any scalar quantity. Temperature is a scalar quantity. Elevation, for example. Concentration of a solute in a solution. Potential energy, for example. And so forth. Let me go ahead and finish sort of drawing these hypothetical contours of our scalar field u, just so it's clear that it's varying everywhere on this plane. And now let's consider moving through this scalar field, this temperature field or concentration field, whatever it is, and we'll move it along a curved path. We'll call this curved path C, and it's an arbitrary path. And let's see, this curve C can be described mathematically as a function x as it varies with parameter s, and I'll tell you what s is in a second, y as it varies with s, and if we had a z component to the curve, it would be how z varies with s. And s is the cumulative distance along the curve. Right? So we might mark off little tick marks of distances along the curve, and at one point s might be 5, the next point it may be 6, the next point it may be 7, and so forth. But s is the cumulative distance along the curve, and so we can describe c as some mathematical function x describing how x changes with cumulative distance, and another function y describing how y changes with this cumulative distance. Now, let's imagine we want to know what is the rate by which u changes along our curved path. So we want to know, as we move through our scalar field along this curved path C, how quickly does u change? And we can quantify that change by the derivative of u with respect to our cumulative distance. So it's the rate change of u per meter or foot of distance along the path. And we know that u changes in x, y, and in general z. And we know that the curve changes. Curve is defined by how it changes with x, y, and I'll go ahead and write z, because in general that's what it'll do. And so we can evaluate this rate change using the chain rule, by using partial derivatives. So the rate change in u with respect to x times how quickly x changes as we move along per meter of increment along the curve, plus the partial of u with respect to y times the rate change that you move in the y direction per meter of distance along the curve, and then the rate change in u with respect to z times the rate at which z changes with s, or the distance along the curve. And you might, if you and we can write this in a more compact form. The rate change in u along the curve is equal to the gradient of u, as we just defined, dotted with dx ds in the I hat direction, dy ds in the j hat direction, plus dz ds in the k hat direction. So in other words, if r is our position vector, on the curve, that is, r is equal to the x in the I hat direction plus y j hat plus z k hat, then this derivative, or this sum of partial derivatives, is this describes how r changes with respect to cumulative distance. So this is the rate change in r with distance. And we can visualize that, for example, if we have our position vector at some location at some value of s. So this is the position vector at some value of s. And if we change s a little bit, then we have the new position vector at s plus ds. Okay, and so the change in r is given by the difference between the two vectors. And maybe I'll use maybe you can see this little white vector is an infinitesimal change in r. And the magnitude of this change in r, the magnitude of vector dr, it's a vector because it's the difference between these two vectors, the magnitude of dr is equal to ds. Okay? And so therefore, dr ds is a unit vector in the direction s hat. So this is a unit vector with s hat tangent to curve C. So we can write this derivative we can rewrite it as, again, du ds is equal to the gradient of u dotted with the unit vector tangent to the curve. So in other words, we can pick any point along the curve, and given the direction of the curve, the tangent of the curve at that point, we just take that vector and multiply it by the gradient, and that product tells us the rate that u is changing at that point on the curve. And it turns out we don't really need a curve at all to tell how quickly something is changing in space. S hat can be a unit vector in any direction. And the product of S hat with the gradient of u tells us how quickly u is changing in that direction. And so for that reason, this is often called the directional derivative. It's a directional derivative. So that's one usage of U, or one property of U. I'm sorry, one usage or property of the gradient applied to a scalar quantity or a scalar field U. So let's look more at what the gradient tells us, and let's look at an isosurface of U. That is a surface along which U is constant. And so this surface is some arbitrary shape, whatever it is. And say we look at a point P on the surface. And let's look at how quickly U is changing in a direction, but S is on a plane that's tangent to the surface. So S hat is on a plane tangent to the surface at point P. So again, we want to find how quickly U is changing in that direction. And to do that, we take the gradient of U and take the dot product with the unit vector pointing in this direction. But since point P is on this isosurface and we're moving parallel to the isosurface in S, then we know that U is not changing, right? Because by definition, U doesn't change on the surface. And remember, we're evaluating how quickly U changes moving an infinitesimal distance parallel to the surface. And with that, U certainly doesn't change no matter which direction you point on that surface. So S can be in any direction on the tangent plane, as long as it's on the tangent plane, then grad U dot S hat is equal to 0. So what does that tell you about, remember we're taking a vector quantity, grad U, dotting in it with another unit vector. So the fact that the dot product equals 0 means that the gradient of U is perpendicular to that tangent plane. Another word for perpendicular is orthogonal or normal to the tangent plane. So that tells us, again, since the dot product is 0, that tells us that U must be normal to the plane. And let's define a new unit vector as n hat as the unit vector normal to the tangent plane. And so with that, let's evaluate how quickly u changes in the n hat direction. And again, to do that, we take the gradient of u dotted with n hat, and that gives the absolute value of the gradient times the magnitude of the gradient times the magnitude of n hat, which is just 1, and the cosine of the angle between n hat and gradient u is 0, right? Because they're both are perpendicular to the tangent plane. So this tells us the magnitude of the gradient of u. So if we return back to the general equation for a directional derivative, this is 0 when s hat, let's see, let me rewrite that. This equals 0 when s hat is parallel to an isosurface and is maximal. The rate change in u as you move a small distance s is maximal. It's maximal when s hat is normal to an isosurface. So the gradient describes the direction and magnitude of greatest increase in our scalar quantity u. So let's consider one more example here. I'm going to sketch another spatial field, scalar field, and this time let's make it something simple or more intuitive, and we'll say it's topography. So this is a constant. It's a contour of constant elevation. Say we'll just say it has an elevation of 10 feet or something like that. And as we continue to map out this topography, we have subsequent contours. Let's say this is the 20-foot contour, and this is the 30-foot contour. Okay, so you can imagine we're on this this hill. It's a elliptical shaped hill, right? And if we face parallel to a contour, then we're not, if we walk in that direction, then it's easy because we're walking on flat ground. But as we rotate closer and closer to directly uphill, which in this case, which is perpendicular to contours, then that gives the gradient of u. So that again, the gradient of u is directed directly uphill in this case. It's perpendicular to the contours directly uphill. So if we were to sketch contours at various places, we would, sorry, if we were to sketch gradients at various places, we would sketch them perpendicular to contours. This is, again, these are directions going directly uphill. And so the other thing we can note is that the magnitude of U is smaller where the contours are farther apart, right? So for example, down here, if we know again that the gradient of U is directed perpendicular to the contours or directly uphill, but the the change in 10 feet from, say, this contour to this contour occurs over a larger distance. So here, the magnitude of U, of grad U, is small. Whereas here, for example, we have the same change in elevation, but it occurs over a relatively short distance. So grad U is larger where contours are closer together. So near here, for example, grad U is relatively large. The same change in U over a shorter distance. So grad U tells you at a given location, the direction and magnitude of the change in U per increment of distance in that direction. Okay, so hopefully this gives you a more intuitive grasp of this mathematical definition of gradient. And by now, if you're given a scalar field, you'll know how to calculate it from this equation, right? And if you're given a picture of a scalar field, like a picture of a set of contours, like we just looked at, you'll be able to tell its direction and estimate its magnitude.